Hi everyone, I'm Eric, and today I'll be talking about my work with Jan Tsai on a model of metric voting motivated by academic hiring. So imagine the following scenario. Suppose the CS department is looking to hire a new faculty member, and so the chair decides to form a hiring committee. And suppose these are the members of the committee. I want to point out that this committee is somewhat CS leaning in the sense that two out of the three members of the committee work in primarily core CS areas, while one works more interdisciplinarily. And because of the background of the committee, one might be worried that the committee is biased in the following way. Suppose because of the growing popularity of economics and computer science as an interdisciplinary field, some of the applicants work in economics, while others work primarily in core CS areas. Of course, all the candidates are of extremely high quality, but the committee might be biased and prefer the candidates who work in CS simply because they're closer in their research fields, even though the field in which one works has little to do with one's quality as a researcher. And so to address this bias and choose the solution might be to initially include an expert in economics in the hiring committee to balance out the backgrounds of the committee members. But of course, as theoreticians, we're not satisfied by this type of wishy-washy answer. So to study the problem more concretely, we consider a model proposed by Feldman et al. In 2020. And in describing this model, first, we'll describe how the committee forms their preferences, and then what the chair has knowledge of. So in this model, experts and candidates are located in a metric space, and these locations represent their features. For example, the horizontal axis on this slide might represent how theoretical one's work is, while the vertical axis might represent how CS or econ leaning one's work is. Throughout this presentation, we'll use E sub I to denote the location of expert I, and C sub J to denote the location of candidate J. In addition to a location in the metric space, each candidate also has a quality that is independent of her location. And an expert evaluates a candidate as the quality of the candidate minus the distance between them. And each expert then forms a personal ranking of the candidates based on these evaluations. So candidates that have higher evaluations from an expert rank higher for this expert than a candidate with a lower evaluation. And here, the distance between two people represents how similar they are in their features. So the smaller the distance, the more similar they are. So what this evaluation is trying to capture is the fact that experts might prefer lower quality candidates simply because they're more similar in their features. And for the sake of brevity, throughout this presentation, I'll use Dij to represent the distance between expert I and candidate J. And so what does the chair have knowledge of or access to? So the chair knows the metric space, and she knows how many candidates will apply for the position. But at this point, she does not know their locations nor their qualities. So with the knowledge of the metric space and knowledge of only the number of candidates and nothing else about them, the chair will choose and commit to a committee of experts. Upon committing to a committee of experts, the location of the candidates are then revealed. I want to note that locations and qualities of the candidates can be arbitrary. In particular, they can be worst case for the chosen committee. Moreover, the chair cannot see the qualities, as indicated by the reddish-orange rectangle on the left, but she can see the locations of the candidates, as indicated by the greenish rectangle on the right. The only information about candidate qualities comes from expert feedback. In the Feldman et al. Paper, each expert truthfully reports their favorite candidate, and the goal is to select a single candidate whose qualities are most epsilon worse than the quality of the best candidate. This difference in quality between the best candidate and the chosen candidate is called the regrets. In our work, we consider a more general problem in which each expert returns a ranking of her top K candidates, and we wish to choose multiple candidates whose cumulative regret is at most epsilon. And for any notation, I will keep in the top right corner, just for easy reference throughout the presentation. So at this point, one might ask, why do we choose to look at rankings rather than approval votes? More specifically, why do we have each expert return information about their favorite candidate, their second favorite, and not just information about, okay, this set of candidates on my top two. And so it turns out if each candidate only returns approval vote, sorry, if each expert only returns approval votes, there's no way to guarantee anything better than constant regret. And so I've given the counterexample for two approval votes on this slide. And basically what happens is that every expert will return the same two votes, namely a vote for candidate one and a vote for candidate two, because they're far better than the rest. However, because every candidate returns the same votes in both worlds, we cannot actually differentiate between the two worlds. And so we'll end up choosing the same candidate in both of them. But if we choose candidate one, then in one world, namely the second one, we get infinite regret. And if we choose candidate two, then in the first world, we incur infinite regret. So at least in one of the worlds, we ended up choosing a bad candidate. And this problem disappears when each expert returns a ranking, because then we'll actually know in each of these worlds that all the experts will prefer candidate one over candidate two. And in the second world, every expert will prefer candidate two over candidate one. And so we can actually differentiate between the two worlds. Now for the model in which each expert returns her favorite candidate, and we only want to choose a single candidate, Feldman et al. Demonstrate the following bounds on the sides of the smallest committee that guarantees that most epsilon regrets for any set of M candidates. What I want to point out about these two bounds is that there's an exponential gap between them. In particular, the lower bound grows linearly in the number of candidates, while the upper bound grows linearly in M to the D, where D is the dimension of the underlying metric space. In our paper, we nearly closed the gap, and we showed that the size of the smallest committee depends only linearly on the number of candidates, but inversely on epsilon to the D. And we say nearly tight because we're actually hiding a constant to the D factor, but this factor is also present in Feldman et al. Bounds. And so there's still an exponential improvement. In fact, the bounds on the previous slide is actually a corollary of a more general result that we've proved for general convex norm spaces. And our general bounds are given in terms of the covering and packing numbers, which for the same radius are only a multiplicative constant to the D opt. And the term that multiplies the covering and packing numbers in our upper and lower bounds are actually off by a multiplicative log K factor. So upper bounds are only off by a multiplicative constant to the D times log K factor. And in this sense, they're nearly tight. Okay, in the remaining time, I want to give an idea of how we achieve our upper and lower bounds. Now I'll do this only for the setting in which each expert returns her favorite candidates, and we're only looking to hire a single candidate. And later on, I'll briefly go over how to generalize the techniques to general K and L. And so for the setting in which K and L are both 1, the upper bound is the covering number times the number of candidates. And so our nearly optimal committee is constructed as follows. First, we'll place a minimum epsilon cover of experts over the metric space. And then we'll consider a spanning tree whose edges are only between experts that are epsilon close. In particular, since this is a spanning tree in which the number of experts is at most the covering number, the number of edges in the spanning tree are also at most the covering number. And so if we place M experts uniformly on each edge, the size of the resulting committee is at most the covering number times N as desired. And since each edge is epsilon length, the committee forms an epsilon over M cover of the spanning tree, which is the one-dimensional space. In contrast, Feldman et al. Place an epsilon over M cover over the entire space, which is d-dimensional. And this is where exponential improvement comes from. And so how does our committee allow us to guarantee low regrets? The first thing to notice is that the epsilon cover will prevent any non-favorited candidate from being more than epsilon better than a favorited candidate. And so we can just ignore all the candidates who did not receive any votes. Moreover, when two experts that are very close to each other have different favorite candidates, we can actually tell the difference in quality of the two candidates up to a very small error. So thus, the epsilon over m cover of the spanning tree will allow us to estimate the difference in quality between any two favorited candidates up to some error by chaining together estimates while walking along the spanning tree and noting whenever we encounter a favorite candidate that we have not seen before on our walk. And so every time we encounter a favorite candidate that we've not seen on the walk, we'll incur an epsilon over m regret. And since the number of times this switch can happen is the most the number of experts, in total, we'll only incur an epsilon error in our estimate. And since our estimates are so close to the regret, we can actually use them as proxies for the regret of choosing a particular candidate. And I want to point out that we know that there exists some candidate for which the left-hand side is at most epsilon, namely the candidate with the highest quality. And so we know that there exists some candidate for which our estimate is at most epsilon. And so if we choose the candidate that minimizes the estimates, then we can choose a candidate whose regret is at most epsilon. And so what happens when each expert returns a ranking of her top K candidates? In this setting, note that even after removing K-1 candidates, we can still carry out the walk process that we carried out in the previous case, because each expert still has at least one candidate in her top K remaining. And so this should sort of remind you of K connectivity in graphs. And indeed, we formalize our arguments using a graph in our paper. And the key property about a K-connected graph that we use is that the diameter of such a graph is at most the number of vertices divided by K. And so the number of times we'll actually have to note the switch in preference along our walk is actually upper bound by n over K instead of m. And so we actually incur only epsilon over K error rather than epsilon. And this is really enabled by the fact that we have more information about the expert preferences. And so what happens when we want to choose multiple candidates? When we can only do this when the number of candidates we want to choose, the most the information that the experts give us, because if L is greater than K, then after we chosen K candidates, we have no information about the rest. And so the candidate we choose can be arbitrarily bad. And so we can only provide meaningful upper bound on the regrets when the number of candidates we want to choose are most the candidates that each expert returns. And so in this setting, when we want to choose more than one candidate, then what we do is we first choose a single candidate, incurring at most this much regret. And then we know that the rest of the problem can be reduced to a problem choosing a candidate when there are n-1 candidates, and each expert returns a ranking of her top K-1 candidates. And so the next candidate we choose will have only this much regret. And so if we continue this process and over choosing L candidates, we'll only incur this much regret, which leads to our general upper bound. And so the remaining time, I'll quickly talk about how we achieve our lower bound for the setting which K and L equal 1. And towards the end, I'll explain how to generalize the bound to arbitrary L and K. And so the idea behind the proof is that we want to show that each ball in an epsilon packing needs to have at least a constant times n number of experts. And so we show that if there is a ball with fewer than constant times n number of experts, then we can construct a set of candidates for which the committee incurs at least epsilon regrets. So our construction proceeds as follows. So for the ball that has too few experts, we'll separate into two spaces. The space within the small ball and then the space in between the two balls. And so we'll place our candidates as follows. We'll place a candidate at the center, and then 1 over C candidates on the boundary of the small ball. And then for each expert in between the two balls, we'll place a candidate at her location. And for each expert within the small ball, we'll place a candidate at her location, as well as 1 over C candidates on the boundary of the small ball. And since we place at most 1/c candidates for each expert inside the ball, and there are fewer than C times N experts within the ball, we place at most M candidates. So this is a valid construction. And what's nice about this construction is that it allows us to vary the qualities of the candidates inside the small ball without changing the reports from the experts. And the way we do this is that the candidates on the boundary of the small ball actually prevent anyone outside of the outside both balls from knowing what's happening within the small ball. And then for the experts that are within the small ball, well, they'll just vote for the candidates at their location. And since the reports don't change between the two worlds, we can't actually differentiate between them. And so we'll choose the same candidate in each location. Sorry, we'll choose the same candidate in both worlds. But note that a candidate that's good in one world is bad in the other. And so regardless of who we choose, in one of the worlds, we'll end up incurring at least epsilon regrets. And so when each expert returns her top K candidate in the form of a ranking, what we'll do is we'll place K candidates in each location that we placed a single candidate before. And so now each expert will basically vote for the K candidates at the same location. And that fills up the ranking. And then we want to choose multiple candidates. Again, we can only choose as many candidates as the amount of information we get from our experts. But when we want to choose multiple candidates, then we'll just note that at least half of the candidates chosen will be bad in one of the worlds. So we'll incur something like omega epsilon times L regret. And so to summarize, in our work, we obtained nearly tight bounds on the size of the smallest committee that guarantees at most epsilon regrets for any set of M candidates. And the upper and lower bound are tight in the sense that they're at most a constant to the D times log K factor off. And these bounds are also for a more general space, in particular general convex norm spaces. Thank you for listening.